This works. Okay, so I'm talking about scalable risk systems. What is a risk system? Um, some of you who've seen me speak previously might know about my admiration for the great moral philosopher Donald Rumsfeld. He got a lot of flack around the time of the Iraq War for talking about known knowns, known unknowns, unknown unknowns. Now, from a risk management perspective, these are surprisingly useful categories. So, known knowns, you really don't need to know much to do much about as a risk manager because you know they're there. So you know how much cash you have in the bank, there's not much you can do about it, it's there. Unknown unknowns, again, you're somewhat limited in what you can do. I mean, by unknown unknowns, that could be anything from, I don't know, flesh-eating plagues, asteroid impacts, the dinosaurs coming back. What are you going to do about that? There's nothing you can do. I mean, to some extent, on the lesser unknown unknowns, like, I don't know, let's say a previously respected European country turns insane and becomes politically unstable, just to pick something completely random out of the air. You can ameliorate some of those unknown unknowns by diversification. That works basically on the idea that there's a correlation matrix, and that works reasonably well if you distribute your assets. It tends to stop working when you have a really big crisis and the correlations all go to 1. But anyway, so neither of these two, the top one or the bottom one, we're going to talk about much. We're going to look more at the known unknowns. Now, I don't know, do we have a largely UK-based audience here? Yes, okay. All right, so if you have a stock position, let's say you have an ISA, and you have, say, 100 shares, you know today that your share position is worth £11,000 if you have it's at 110. That's lovely. And if you look at the price of the shares, they can go up, which is great, or they can go down, which is less great. But this is what I mean by known unknown. We don't know the share price tomorrow or in a year's time. If we did, we wouldn't be here right now. We'd have retired to an island. So we can manage these risks. And I'm a derivatives guy, so I'm going to tell you that the great way to manage these risks is to buy a put option. And then your risks look like this. And so it's fantastic, right? I mean, the value of your shares can still go up, but it can't drop below a certain value. It's fantastic. Now, options are one of those things called derivatives, and derivatives get a lot of bad press in the world. You know, there's the global financial crisis 1, and possibly global financial crisis 2, and CDO squared and all those things. It's true that derivatives can exacerbate risks in certain circumstances, mainly by increasing leverage. But then they can also be useful tools. Like in this case, if you want to retire on this pension portfolio, then it's quite useful if it doesn't drop to 0 because somebody made a bad decision. The other thing, bless you, to bear in mind about derivatives is that they have a reputation for being very, bless you, complex. And if you've ever Googled Black-Scholes, this is what you come up with, and it looks like a terribly complicated formula. And it's, you know, I can't do this in my head. I can't price you an option like this without looking at a computer. In fact, I probably wouldn't even want to do it with a calculator, but we have computers, and a system that looks at your trades, your positions, your derivatives, and calculates the value and risk factors of these things is what I'd call a risk management system. And so let's look at why my mouse isn't working again. Okay, let's look at a slightly historical perspective. So this is one of those weird synchronicities of software and hardware that I sometimes marvel at. So risk management systems as we know them kind of started in the late 70s, early 80s, for two reasons. One is there was a technological breakthrough in the form of Black-Scholes, which allowed people to price options and do it in a systematic fashion. The other one was that computers became available that weren't the size of this room. And so that was interesting. And at the very beginning, this idea that you'd use a computer in trading was considered a trade secret. It was considered a really competitive advantage. I remember talking to some people in Chicago who told me the story that they had their first Sun workstations delivered in the middle of the night and then spent the whole night shredding the boxes so that nobody else on the exchange would find out about the fact that they were using computers to price options. So these things started off in those days. And I hate to say this, they started off as spreadsheets. And my mouse isn't working. And a simple spreadsheet like this could look, a spreadsheet could look a little bit like this. You have a lot of information on here. You have ticker, stock prices. You have some option positions. You have some Greeks. And this is much better than trying to calculate things by hand. So there's that. And it's very easy to get started. Users have a lot of control. That's an upside. On the downside, if you've ever met a user, users having control is not necessarily an unalloyed advantage. It's very easy for people to make mistakes. It's very hard to find mistakes in spreadsheets because they're very hard to test. They're written by people who have no idea about how to structure things in a way that makes them testable. There's no sharing of data between spreadsheets if you keep it simple. And then finally, local calculations are a big problem. So I was thinking about proposing a lemma, but that's probably slightly too strong. But it's basically along the lines of, on any sufficiently large trading floor, there exists at least one trader who has at least one spreadsheet that will bring the fastest desktop PC you can buy to its knees. And he probably wants to run 3 of them in parallel. So local calculations, it's great if you have the spare capacity, but if you have a trader's desktop, it really isn't a good idea. So people moved on slightly. Oops. Okay. And they started addressing the sharing issue. So you start off, you have a database behind it, and that helps slightly. It addresses the sharing issue, so you can share positions. It's a step in the right direction. It doesn't address the user control issues. It doesn't address the... That's useful, thank you. Sorry. There's so much for trying out new software in the middle of a presentation. So it doesn't address the user control issues, and the spreadsheet problems are still spreadsheet problems. So people moved on slightly and started building client-server systems. So this is kind of the sort of system I was working on at Citibank in the 90s. You have lots of clients that are relatively thin. Is that me? The other tab? Sorry. Go away. Thank you. Thank you for solving my tech problem. Live on stage, fantastic, appreciate it. You have, the key thing about this architecture is that the calculations are moved from the client to the server. Also, we're moving away from spreadsheets. That's a huge step forward, but the moving calculations to the server has the benefit that you don't lock up your client machines anymore, but it also brings its own problems. So for example, the server process is now immensely complicated because it has to deal with concurrency, It has to serve multiple client requests at the same time. It has to do risk calculations as fast as possible. And it's still limited by one box. So in those days, I have no idea how much the server we had at the time cost, but it was the size of a small refrigerator. It had several gigabytes of memory, which astonished me at the time. And it must have cost comfortably in the six figures. And the real problem was that it was the fastest machine we could buy. We had gone to HP and said, give us your fastest box. So if we reach capacity of this box, then that's it. So it's a better system. It's more scalable than the previous one, but it's not scalable enough in the long term. The other thing I kind of just want to point out here is that we have. Does that work? No, it doesn't work either. So on the right, we have kind of trade feeds coming into the system. We have market data feeds. Data flows into the database, and then down here we have stuff coming out to other systems. So we're kind of tied into a web of other systems, just something to point out. So let's move on to client server. Yeah, okay, centralized compute. We have control. We're not overloading our clients, but as I said, we're still limited by complexity, and it's not as scalable as we'd like it to be in the end. Which takes us to an underappreciated software design philosopher, Mr. Heath-Robinson. So at the same time as people started building proper multi-threaded client-server systems, people also tried to make spreadsheets be more useful, and that led to a number of interesting designs. Is anybody familiar with Heath-Robinson? He basically drew fantastical machines that do simple things in the most complicated way possible. And if you're trying to make Excel, which is a wonderful tool, do a job that it's not designed to do, then you end up with this kind of architecture. Now, this is the kind of thing people talk about in the pub towards closing time, when they reveal that at one point they were responsible for these sort of things. So on the moderately sane side of things, putting a custom grid behind your Excel spreadsheets, that actually solves a problem. It gets rid of the local calculation, it allows you to share infrastructure, that's actually not so bad. In theory, it very much depends on the quality of the implementation, and that varies considerably. Custom infrastructure about version control, starting Excel sheets, stopping Excel sheets, building custom infrastructure to feed market data into spreadsheets and all that kind of stuff is kind of standard stuff in the city, I think, still. And then on the special kind of prize goes to a certain unnamed bank that I didn't work for myself, so I'm not responsible for this, but my ex-boss was very proud of the fact that he managed to take spreadsheets and run them on a server farm overnight to do the risk processing for the bank, where you just have to shake your head and go like, how do you come up with this as a design decision? Another notable, interesting architecture is another bank in Canary Wharf, the one with the blue logo, that has a custom functional programming language implemented in Excel, on top of Excel, again to solve some problem, probably the problem that there was somebody who really wanted to implement a functional programming language. But yeah, so I just wanted to draw your attention to this. The stuff is out there. If you get a job in finance, you might end up working on this. But for now, let's forget about it and move on to something moderately sane. So on the client-server issue, the big problems that we had was still the complexity and also the lack of scalability, right? You only have one computer, and the computer doesn't grow. So the way to get around that is to have a distributed system. Oops. Now, this looks a lot more complex than the last slide because I've broken things out a little bit. But let's talk about what goes on here. So I've broken down the market feeds into kind of different things, just to show all the different parts that go into a system. Mainly talking about equities because that's the majority of my expertise, but I've spent enough time in other asset classes to tell you that it's basically the same. So what is going on here? So we have data coming in. We have trades coming in. Now, trades need to be processed and written to a database, and then they need to be aggregated into positions, and we're going to talk about positions a little bit more later. Over here, we have our clients, shouty traders, risk managers, all sorts of people. We have some downstreams databases here, and then we have the core of the distributed system, right? So we want to take our calculations and split them up and distribute them across as many computers as we have access to. This is purely coincidentally remarkably similar to a system I worked on at Gebrüder Lehmann until about 2008 when I stopped working there. It was fairly scalable. I mean, it didn't scale easily because it wasn't originally designed to scale beyond certain points. But we got up to 600 workers or something in London. So it was, by pre-internet standards, it was a reasonably sized system. Now, so what goes on here? We have a risk controller that kind of coordinates everything. It creates jobs, puts them onto the input queue, then the workers just sit there and go like, give me a job, process it, here's the results. Give me a job, process it, here are the results. Scales up nicely until it turns out that the risk controller runs out of memory, and then you have to do some technical debt alleviation and end up with a risk controller that you can scale horizontally so you can have multiple entry points. But fundamentally, the architecture is kind of broadly sound. Now, let's look at that, what's going on in the risk controller slightly more. No, this is irritating. Right. So this is what goes on in the risk controller. Forever, we get a snapshot of the market data. We get a snapshot of our positions. We split the combination of market data and positions into a number of different jobs, push those onto the queue, and then wait for the results back, do a little bit of post-processing, and go back to what we were doing before. Now, this is obviously very high level. There's a lot of stuff we can gloss over here. Splitting the jobs is probably worthy of its own hour talk, because you have to be, well, there's a lot of different choices you can make, and they have different impacts. So if you have a homogeneous pool of workers, it's quite important that the size of the individual jobs is roughly the same, because otherwise you end up with one worker still busy on a long job while the others are all finished, and that slows down your whole calculation. So if you have a very heterogeneous portfolio of products, you have to be quite careful about how you design that. In this case, we used a particular trick, which is that it's really more an organizational trick than a technical trick. We basically dedicated groups of calculation engines to different desks. And that, from a technical perspective, solves the problem that the vanilla traders who have simple trades to price that calculate very quickly don't want to wait for the exotics traders that have slower trades to price. That's the technological problem. So we end up with much more consistent chunk sizes. The reason I call it a social hack is because it means that when a trader complains that the system is too slow, you just have to go to that trader and say, well, if you pay me more money, I can give you more machines that will just help you out. And that worked remarkably well. I mean, we had a lot of issues with our traders, but lack of money for new machines was not one of them. Speaking of new machines, this is kind of interesting because the limiting factor we hit at the end wasn't really so much that we couldn't scale the system up. It was that we couldn't physically buy more machines. Our data center was full. So for the younger people here, this might seem bizarre, but in those days, you had a really discontinuous scaling function, right? So you started with one computer, it's cheap. You add another computer, it's linear. You have to move your computers to a data center, there's a cost jump, and then it's linear again. And then your data center is full, and you have to build another data center, and all of a sudden, there's a huge cost jump. So that's kind of where we ended up with that. And now, does this work now? Excellent. So pros, it's a lot more scalable. It's still limited by physical hardware, and it was a pretty complex system. I really didn't see a lot of my wife and daughter while I was working there, and we had kind of, yeah, it was an ugly baby. It was my baby, but it was adopted, so I won't take all the blame. But it was still my baby. I was responsible. So that's kind of where we are. The future. I really should have put a slide in there, a picture in there. Okay. So we've kind of talked about where we've been in our risk management system journey. And one of the things I've raised over and over again is scalability. The other thing, as a bear of little brain who has had to debug these systems at 3 o'clock in the morning, one of my key goals in life is simplicity. I like to keep things simple because I know that they will break, and when they break, I have to fix them at short notice. So I want things to be easy to understand. I want things to be easy to test and debug. So how do we think we can achieve that? Well, let's take a step back and think. I mean, I've kind of given you some examples of risk systems, but let's just take a 10,000 feet view of what really the core functions of a risk system are. So we have trades coming in. Trades are kind of the lifeblood of this thing, right? So we have our contracts, our trades. The very first thing we need to do is capture those things. I mean, they're part of the books and records of the company. It's kind of essential that we capture them. Fine. Then, once we've captured the trades, we need to aggregate them. Trades, there are thousands and thousands of trades coming in every day. Nobody can make head or tail of just looking at a list of trades. It doesn't, it's data, it's not information. So we need to somehow aggregate these trades into a meaningful view of positions, and we'll get to see that different people in the organizations will have a very different view of what constitutes meaningful positions. But so far, we've kind of just rearranged the data. Now we need to go do our actual bread and butter risk calculation, and we know we need to see that at the position level at some point. So how do we get, and then, of course, consistency. Consistency is one of the key requirements. So if you go back, I can't go back with that mouse, it's terrible. If you go back to the risk loop, the risk loop takes the snapshots at the beginning of everything because it needs to be consistent, right? There's no point calculating the risk for position A at 11.27, and then the risk for position B at 11.28 with different market data, because they won't add up. It doesn't make any sense. It's hard to explain, but it's completely meaningless if you're not consistent. So consistency is key. Because if you think about it, everything changes, right? We're in a financial market. Literally everything changes around us all the time. What do I mean by that? Let's have a look. So let's look at Black-Scholes again. We'll look at the simplified version because we don't care about the math. And we don't actually care that it's Black-Scholes either. The same thing applies to every other pricing model. They all take all these inputs. Some take some more esoteric other inputs that we don't worry about. So what goes into pricing a derivative? Well, first of all, there's some information about the derivative. Well, no, actually, let's do the other way around. First of all, there's the price of the underlying. There's time to expiry, interest rates, dividends, volatility, and strike price. And there's variations on this, but this kind of applies to everything. How often do these things change? Well, stock prices on modern exchange change in, I don't know, infinitesimally small time. I mean, nanoseconds between orders. I mean, it could be ridiculously fast. We probably don't care that they change that fast, but they do change very quickly. Interest rates, similarly, on modern exchanges can change very, very frequently. Dividends are interesting because they're in the known unknowns category to some extent. So there are very different kinds of dividends. Once a company has declared a dividend, it's kind of a known. Until the company has actually declared the dividend, it's an estimate, and it might change whenever the analyst that's assigned to it has decided to update it. Volatility, again, it's philosophically even more tenuous because the whole concept of volatility is A, made up, and B, logically inconsistent when you start talking about Black-Scholes and vol surfaces. If you want to know about that, grab me afterwards for a beer or something. It's quite funny. So these things all change. The thing that we haven't talked about yet is, well, time. Time changes too. Usually once a day. When you take a day off, the time to expiry. K comes from the instrument, right? It's a strike price. If you think back to the third slide, I sold you a put option at £110. That's the K. And you think, well, that's fixed, right? It isn't. Instruments change too. This is what I mean, everything changes. Literally, there's nothing fixed in this world. Instruments change too. Instruments don't change as often as market data, but they do change. And they change for various reasons. So if you owe the bank enough money, then it's their problem rather than your problem, and the bank will be in a position to renegotiate things with you. If you're a good enough customer, they will find a leeway of keeping you as a customer sometimes. More importantly, derivative contracts, when they get a bit complicated, have state changes. So if you have a ratchet option, the state pre-ratchet and post-ratchet is different. You could very easily have an instrument that depends entirely on the client making a decision at some point. I want to exercise this option now, and that you have to record, and obviously the valuation before and afterwards is very different. And then even the simplest instrument, even something as simple as a share, can change dramatically. This is based on a real example. Names have been changed to protect the innocent, or the guilty. So anecdote time. So I came into work, 7:30, Lehman Brothers, and the traders were shouting because their share prices and their option prices were all looking wrong for this big French company. And they said, it's the system's fault. Why haven't you fixed it? Why is the system broken? It's always broken. It's always your fault. Go and fix it. So we dug into this, and we found out that this big French company had done something very creative from a corporate finance perspective. And it had decided to do three things at the same time. First of all, it has done a share split, a 4-for-1 share split. Then it had decided to issue another company shares, so have a spin-out company. So if you had one share, you were entitled to 1/10 of a share of the new company. And just to make things really complicated, it had added a special dividend in cash. Now, this is complicated enough if you just have a position in the actual shares, right? Because all of a sudden you have a position in different shares. You have to recalculate everything. You have a cash position that you didn't have a minute ago. Now, imagine if you've sold an option on this share. What is the strike price now? I don't even know. So all I'm trying to say is everything changes, including instruments. So one of the key things that I like to see in a modern risk system is a version data source. So basically, my philosophy for the system is that everything is versioned. So we're going to do this very simply. So every bit of data in the system has a simple key. It has an object type. So this could be equity spot, vanilla call option, whatever. It has an object ID. Doesn't really matter what it is, as long as it's unique. So why not use a UUID, right? It works. It's there. It's unique-ish. And then it has a timestamp. And again, the timestamp itself isn't really that important, but as long as it's unique and monotonically increasing. Again, so at the moment I'm using date times, but we could just use integers instead. Well, is there a difference between an integer and a date time? Not really. It's all seconds. And then sometimes it's useful to have a breakdown between, say, the real world or in some scenario or projection. So it's useful to tag a scenario at the end, and then we can do what-if analysis. We can say, what happens if I book this trade, but it's not actually going to flow through? What happens if, I don't know, the pound rises by 20% or something? We can do scenario analysis. Key things here is the unique identification. Data, once it's in the system, is immutable, and values are interpolated forwards. So this is something based on what's called previous tick interpolation. That comes from the time series analysis world, but it's really simple to understand. So if at 8:27 I ask for the value of A, I get 1 back. If at 8:30 I ask for the value of A, well, it hasn't changed, I still get 1 back. If I ask for the value of B, I don't get a value back because it's an error, and so forth, right? So this is fairly simple, straightforward. But the key thing is I can always go back and say, I ran this calculation for instrument XYZ at timestamp Y, and I can always go back and rerun that calculation exactly as it is, which means I don't have any of the problems I've had through my life, where it works on my machine, it doesn't work on your machine, it works on the grid, it doesn't work on this grid. The other thing, well, this is kind of a side benefit, it's not really the main driver. We can pass around the keys. Keys are quite short compared to some of the data we pass around. Then again, they're quite long compared to other data that we pass around. Caching is really quite trivial now, if you think about it. Because at any point, anywhere in the system, you can just say get and give me the key for this type ID timestamp scenario. And then this, whether this connects straight to different upstream systems, whether it connects to a local cache then a non-local cache, and then to the systems, is really completely irrelevant. This is just a performance optimization, right? This, from the perspective of the client, it really doesn't matter. We can just say, I want this globally unique identified bit of data, and you'll get it. Yes, and that's kind of it. So, let's go back. So this is kind of a key decision on how we do things. Let's go back to looking at what we need to do. Let's look at trade processing. So trade processing is really, as I said earlier, really quite simple. It's crucial that it's done right, because this is the main input source into the system. These are legal books and records, and you want to make sure that you get them right. So if you get an order coming, a fill coming through for an exchange, and it doesn't make it into your trade store, that's a problem. Because then that means you have well, at the very best, it means that somebody just has to manually reconcile these things. It's extra work and so forth. Worst case, it could mean you just get sued for a lot of money, because somebody sold you something, you haven't bought it, you haven't paid. Bad things happen. So but the key thing here is that the orders, the order of magnitude of trades can be staggeringly high. So if you think about it as even a slow manual trader could just issue an order to sell, I don't know, 10,000 IBM shares, right? Simple stuff, happens hundreds of times a day. Those 10,000 IBM shares could come back as one fill, theoretically, 2 fills, 5 fills, 1,000 fills, who knows? It's, but really, there's a 3 orders of magnitude between number of orders and number of fills coming back. And that's just for one order, if you think about it. Yes? So so the trader says, I want to sell 1,000 widgets, and then yes, exactly, yes. And then there's a lot of subtleties around how you actually present that order to the market. If you carry a big sign saying, I desperately want to sell 1,000 widgets, the price of widgets is probably going to drop. So so then there's an order management system which is going to try and iceberg it or whatever. Yes. Yeah. It's okay. Thank you. So as I said, the only real problem here is A, making sure it works, and B, coping with the sheer volume. The volume was kind of a problem 20 years ago. These days, we probably don't have to worry about it too much anymore. I mean, databases well, maybe not relational databases, but certainly object databases, JSON data stores are fast enough to cope with all this sort of thing, mainly because the people that built them deal with even bigger data volumes. So we can just piggyback on that.
You're probably only talking about 10 million records a day.
Yeah, trivial, small data. It almost fits into a spreadsheet. So the question then is what happens with these trades after we've captured them and got them into our system? And this takes us to position aggregation. Now, if we're thinking about our 10,000 widgets, you get the fills back for these widgets, and you think, well, that's nice and easy. We just add them up, and that's our position, right? It's not quite as simple as that. This is becoming kind of my refrain today, isn't it? It's not quite as simple as that. Let's go through an example. So let's say we have 2 traders, Fred and Joe, And they sell and buy shares in companies A and B to two of their famous customers. So Fred buys 100 shares of A, Fred buys 100 shares of B, Joe sells 100 shares of A, and so forth, right? Nice and simple example. Two traders, two trades. And so from Fred's view, at the end of the day, his position is this, right? He's bought two sets of shares, great. Joe's view is that, well, he's sold 100 shares and bought 100 shares, great. So we've aggregated the positions, wonderful. It's great for the traders, and there's probably, if they work for the same desk, there's another layer of aggregation we want to do here for the head of desk and the head of the floor and so forth. But that's a nice, simple view. But there are other people in the company that are arguably even more important than Fred and Joe. And for example, there's the head of market risk. Now, the head of market risk looks at the positions in shares A and B, and he says, well, I have 0 net position in share A. I don't care. Let's just not even bother calculating that. I have 200 shares in B. Okay, that's a risk I need to look at. The counterparty risk manager is going to look at, well, Mega owes us 5,000 euros, and Giga owes us 19,000 euros. That's a position we need to look at. So the point I'm trying to make is that trade processing has to be fast, but is relatively simple. Position aggregation is much more complicated, and really, ideally, it'd almost be an ad hoc process, right? You want users to be able to define a view of the world of how they want positions to be aggregated, as and when they like. So for example, if the corporate risk manager heard a rumor that companies A and B are thinking about a merger, he might want to change his aggregation view, right, and see what happens if these two companies merge. So trade processing has to be fast and efficient. Position processing has to be flexible. So that's just something to look at. So let me continue that. We have a slight problem in the way we've done it so far. So trade processing, yeah, okay, that's fast. Then we need to do position aggregation, which we've just discovered is complicated and slow. And then we're going to do calculations based on the top of this, and that's really tedious. But thankfully, we can break this down. So position level calculation boils down into an instrument level calculation, which is really slow and complicated and needs quants and mathematicians. And then it's just a simple scaling by position size. So really, what we need for our risk calculation isn't a set of positions, it's a set of instruments. And if we look at that, so this is the kind of traditional loop of how we do things. We get the trade in, aggregate the positions, calculate it, publish the results. We can simplify that dramatically by saying we get the trade in, put it into the trade database, forget about it. We look at the instrument that's coming in from the trade and add that to our live instrument set, calculate the instruments that we want to look at, save the results here, and then the position scaling we can kind of do offline, right? So this is in the calculation loop and happens as fast as possible. This is offline and happens kind of on user demand, much, much, much simpler. The live instrument set is interesting. So what we need to know, we need to calculate the risk for every instrument that we could conceivably have a position in any conceivable, sane position view of the world, which sounds really complicated. But actually it's trivial, because we just say, well, what instruments can we have positions in? Well, we can have positions in an instrument that we had yesterday, and any instrument we've traded since. That's kind of by definition. And to be honest, we don't really care about, we have a lower bound on the number of instruments we want to calculate. If we have a system that scales up, then we don't really care about having a strict upper bound. If we calculate some instruments that we don't care about, well, that's going to be really expensive. It's going to be like minutes of Amazon compute time. That's really going to add up, right? So this is quite liberating. We don't have to worry about that anymore. There we go. So that's our trade processing position aggregation. Yep, good. Now, if we go back to the Calc Loop we're talking about, this is what I was just explaining. So this is the Calc Loop where we were doing it the old way, where we were snapshotting positions and snapshotting market data. We split the jobs, and it looks like we're pushing a lot of data around here. If we look at the if we look at the new style Calc Loop, then well, it looks quite similar, but it's much simpler if you drill into it. So here we create the timestamp, just an arbitrary marker in time. We get the live instrument set as of this timestamp, and then here we split the jobs, push them onto the results, wait for the results queue to come back, and the nice thing about this is that if you look at it, the calculation spec is really simple and really small. So what do we send to a client, to the worker on the job queue? We just give it an ID because it's nice for things to have IDs. We give it a list of keys. If you recall, the key is, the type of instrument we want to calculate, the identifier of the instrument, the timestamp, and possibly a scenario. We give it a market data timestamp. It's quite useful to segregate the timestamp for the instruments from the timestamp for the market data. So quite often you want to do, say, an analysis of, these are my positions as of today. What happens if I roll the market data forward to tomorrow? You can do that in some things. So that's just something to pull out. The scenario shouldn't be on there. And indicators is just a set of things we want to calculate. So it might be present value, delta, gamma, vega, theta, and any of the variations thereof. But the key thing is that the versioning of every instrument here makes life a lot easier, of every object. And this is if anybody knows how to convince GraphViz to organize things, to lay out things nicer, please tell me, because it seems to be a bit random. So this is a graphical representation of the little Calc Loop we're just talking about. We start off with a set of instruments we want to calculate. The controller does its loop thing. It creates jobs, puts them onto the queue. The workers get the keys off the queue, give them the keys of stuff they want to calculate, or give them the data that they want to calculate. They can just go to the data provider, the multi-level cache that we talked about earlier, and do their work as fast as possible, push the results into the results queue, go back to the controller. Actually, as I was drawing this last night, I realized that this isn't really necessary, technically. So they could just write the results back straight to the results store and just notify the controller, which would, just notify the controller that they're done, which means that we have a distributed write rather than a write from one central location, and just makes life easier and simpler, and it means that the controller has one less thing to do, which is good. Simpler, much easier. Right, where are we going next? Yeah, so that takes us to the design principles. We have, every component should ideally have a single responsibility. Versioning and immutability is what I've just been talking about. Caching, loose coupling. I mean, these are all like a little bit like motherhood and apple pie as design principles, but I think they stand up. And this is kind of the whole set of the architecture. So just to cap through that again, we have trade feeds coming in, we have a trade processor that puts it into the trade store. From the trade store, we can get the set of live instruments for the controller. The controller builds jobs, puts them onto the queue. Workers, this can scale up nicely parallel, calculate the results and push them onto the results queue. And then the position aggregation is happening off to the side of things and out of the main Calc Loop. Okay, so much for the theory. Where's my architecture in practice? So I have a working skeleton that ties it all together, and it's a proof of concept. And it will get better and more complete, but basically I've demonstrated to myself that this works nicely and scales up. One interesting thing is, of course, how you map this architecture onto, well, it's not hardware anymore, is it? How you map it onto cloud systems and cloud components. So far, I've kind of taken the simplest possible approach. So for the queue, I'm using SQS because it's there. For the data providers, I'm using DynamoDB because it's very simple to build a schema and build a version data store on top of DynamoDB. It's a bit disappointing that I haven't been able to find a version data store out of the box. Maybe there is one. It'd be nicer. And I mean, if I was building this in a real production environment, there's a whole host of things you need to consider that I'm blithely ignoring because I'm doing this in my spare time. So for example, I haven't even investigated the performance characteristics beyond, yeah, it works. And if you look at, the kind of job queues, if you look at where we want to cache things, there's just a myriad of options you can look at for doing that. If you look at what a lot of these things do, I mean, this is kind of almost these days so simple that it doesn't need a process anymore. You just need to have something that translates the data format of the trade feed into the data format you want to store. You could do this either using a dedicated process, you could do it using AWS Lambdas, you could do it, I don't know, lots of other options. Yeah, and that's kind of it. So I'll leave this up here for you to look at, and any questions? Yes? Mm.
Which becomes again quite complicated. You have several lines which you're giving the systems, so they have maybe the same scenario, but actually they will have very different sort of actual things like the price. How do you manage this complexity as well? Do you still kind of go with even for the third thing?
So, so the way I've started doing that for this is that I've kind of designed my quant library, to give it a fancy name, so that every instrument knows what data it depends on. So if you get an instrument in, you say, what data do I need to price this? So that would then give you back a set of identifiers, and you could then map that onto a scenario definition. So if your scenario definition says these spot prices go up by 10%, you just need to map between those two items and apply the transformation. I mean, let's talk about it offline. It's probably better to draw these things. Yeah. Sorry. Yes.
What programming languages are you using to implement this stuff?
For this, I'm just using Python because it's Python. No, I'm doing this for fun. Why would I not be using Python? But mainly, I'm using AWS. There's a lovely Boto 3 library that gives me an interface to the AWS APIs, and it's fast enough for what I want to do. If I was doing this for real, I'd probably still use Python until you give me a good reason not to. Yeah, Paul.
But one observation, obviously this works for securities.
Mm-hmm.
For OTCs, you end up with one instrument per trade, so the separation of the two is slightly less bad.
Yes, and this is kind of what I was talking about when I said that the model applies to kind of all different asset classes. I think even with OTCs, I find it useful to have the distinction between instrument and position, even if you end up having only one instrument for each position. But, one position per instrument, mainly because it just means you have to have one mental model, one data model rather than different ones. And
We'll get some clustering of similar stripes, similar
yeah,
FX options, that sort of.
yeah. And also, the last time I did OTCs like that, we ended up back-to-backing them between legal entities. Not at all for tax reasons, of course. And so you end up with every OTC having at least 3 trades attached to it anyway. But the clustering is interesting because if you think about the worker, so I briefly alluded to that about how do you split jobs, and I talked about job sizes. The other thing that's really quite crucial in splitting up jobs to workers is data locality, right? So if you have instruments that need chunky data beyond just like a volatility and a strike and a spot price, if you have something that needs like a correlation matrix, then it makes a lot of sense to try and group all the jobs that need the same data, because then this worker here just needs to go to the data provider once, keep and cache the data locally or reuse it in the same job. But like I said, this is kind of where it gets really, it really depends on the product you're pricing, and you need to think very hard about how fast your data access is versus how fast your calculation times are and so forth. Cool. Yes? Well, are there technical changes? If I was being facetious, I'd say no. It's like, computers are still x86 and using the same underlying processor. I think that the perspective has changed slightly. So yes, there are some things which are available out of the box now that would have been a bit trickier 10 years ago. So for example, I can spin up a local stack image on my laptop. I have essentially access to all the AWS services. 10 years ago, setting up a development environment for free that gives you, a reliable queue service, a reliable database service, and so forth, would have been a lot harder. I think the other nice thing is that this is kind of where it really comes in. When I start stress testing this kind of system and scalability testing it, and I want to go from 5 workers to 5,000 workers, I can do that now. I couldn't do that 10 years ago. But was the architecture possible before? Yes. Would I have seen it 10 years ago? Maybe not. Yes, absolutely. That makes sense. Yes.
The risk calculation you have is a function of 6 or so variables which change at massively different rates.
Yes.
That looks like the sort of standard case where partial evaluation is really effective. Do
Hmm.
you compute everything from scratch when the data changes, or do you try to incrementally update based on your previous results?
Yeah, that's a good observation. So, no, that's the wrong one. Where's my...
Depends a bit on the model. Something can hash intermediate results, and other things you have to stuff them into Spreadsheet.
let's not worry about that.
Intermediate result is take the model and specialize it on data which is not varying very quickly, and use essentially a fast model rather than data which is varying more quickly.
Yes. I think that's a very good observation. And depending on the use case, it might be useful or not. I think the problem you have is that the models... I mean, I've seen something like this done before. I've seen, I mean, you can use what's the rule, the Taylor rule and so forth to do approximations. If you want to do tick-by-tick recalculation, you can, I've even seen somebody who built a multidimensional risk cube and then did interpolation between those points. So your calculation just becomes a simple array lookup, or an average. In the context I was kind of thinking about for this system, you find that the models that take a long time to calculate are the ones you worry about, are Monte Carlo simulations. So it's kind of difficult for me to think about how you'd specialize a Monte Carlo calculation to work more quickly in this context. What you could do, again, nowadays, is use GPUs and just plug those in as specialized workers. That'd be possibly more useful. But yeah, good idea.
You do get some models which do an awful lot of complicated setup. They'll calibrate and reset parameters based on the quality of service and forward curve. And then if you can cache those traveled parameters, then you don't have to do that every time.
Yeah,
That's the same.
yeah, it's a lot of stuff to do. Cool. Any other questions? We have time.
You talk about the data store. This thing will spit out an awful lot of sensitivities and an awful lot of data.
Yes. If we go back to the end, so at the moment, as I said, I'm kind of using Dynamo throughout because Dynamo is available, and it's once you get used to it, it's easy enough to program. I mean, this at the moment is only looking at risk calculations, intraday risk calculations. So basically, you end up with a result store where you have a set of risk for every 5 minutes or whatever it is. Then the next thing you need to look at from that would be a downstream system where you use that for P&L calculations and so forth. And other downstream feeds in terms of regulatory risk and all the kind of gubbins that hangs off the end of that. In terms of the data stores for that, I think the kind of version simple data store with not much of a schema is great at this level. For P&L, I'd be tempted to go back to a relational database, just because it means that you can then write your P&L calc in SQL and do aggregation and stuff like that. But I haven't had a chance to try out the Amazon SQL databases yet. So, does anybody out here has anybody used the Amazon SQL stores? No? Okay. Clearly cool kids don't do SQL anymore.
Cool kids are storing gigabytes of JSON on their HDFS clusters.
Yes. Yeah. Cool. Unless there's any more questions, I'm here tomorrow find me and grab me when you need me. Thank you very much for coming to my talk.